Hello, hello. This is exciting because today we're taking our first step into a BC Calculus specific subject. We're doing integration by parts. Our learning objective today is to practice ultraviolet voodoo. In Calculus AB, we explored integration rules that were inverse operations of the basic derivative rules. Then we saw how U substitution reversed the chain rule. Now we get to see how integration by parts reduces the product rule. This new method of integration is mainly used for products of algebraic and transcendental functions, so be watching for those. So we've got two different functions, u and v, that are both functions of x. And then by use of the product rule, if I were to take the derivative of u and v, those are two different functions being multiplied together, I would take the derivative of the first times the second plus the derivative of the second times the first. Now, if I want to undo that, I would integrate both sides. So the integral and the derivative kind of cancel each other out. Those are inverse functions. And then on the right side, we can split that into two integrals. So if we clean it up a little bit, it looks like this. And then we're going to rearrange things, subtract u prime v from both sides. Now, this probably looks like gobbledygook to you, but this is what we're going to be using. And just stop and look what we have. We have a function, u, and the derivative of a different function. So the formula for integration by parts is this one that we just came up with. I used the product rule and then undid the product rule and came up with that. Or you can write it like this. So the antiderivative of a first function, and then in there with it is the derivative of a second function. You see that? Equals, so the two functions multiply together, minus the second function times the derivative of the first function. So you can see how the product rule is all involved in this. So we have to choose u and v, or maybe more specifically, u and dv to begin with. So we'll let dv be the more complicated part of the integrand that can easily be integrated. And we'll let u be the part of the integrand whose derivative du is a simpler function than u. To choose things for u, you're going to look first for a logarithmic function, then an inverse trig function, then an algebraic function, then a trig function, then an exponential function, liate. So this is sort of your like, who gets to be u first? Now you only have two choices. So if one doesn't work, that's okay. Just try the other one. To help organize this, it's nice to have these tables here where you have u and below it, its derivative, v and below it, its derivative. First thing we're going to do is choose u. So let's look down at the bottom here at liate. Is there a logarithmic function in x e to the x dx? No. Is there an inverse trig function? No. Is there an algebraic function? Ah, yes, there is. That's like the polynomial stuff. So I'm going to let u be x. Now the rest of it, so that's u, the rest of it is dv. Okay, so on dv, I just put in whatever's left over, e to the x dx. Now I'm going to take the derivative of x, which is dx, and the antiderivative of dv, which is e to the x. this was our formula. So u dv equals, let's color it, uv, the two original functions being multiplied together. So x times e to the x, so let's write that down, minus v du. So that would be the antiderivative of e to the x dx. Now look, this right here, antiderivative of e to the x dx, we know what that is. It's e to the x. So our final answer is x e to the x minus e to the x plus c. Okay, let's do part B. Look down at Lie8 and also look at our function. So the antiderivative of ln x dx. Okay, do we have a logarithmic function? Oh, yes we do. So we're going to let u equal the logarithmic function, which is ln of x, and then dv is going to be whatever's left over. So that's just dx. Okay, now we'll take the derivative of ln of x, which is 1 over x dx, and the antiderivative of dx, which is x. Now we just get to use our formula. So we'll start with uv, the two main functions multiplied together, minus the antiderivative of v du, x over x dx. X over x is just 1, so the antiderivative of 1 is x. So our final answer is x ln x minus x plus c. Now we have a definite integral. See this? We're going from 0 to 4. But we're going to follow the same process. So do we have a logarithmic function? No. Inverse trig? No. Algebraic? Yes, we do. That's the x right there. So that's going to be our u. And then dv is going to be the rest of it. Take the derivative of x is dx. Take the antiderivative of dv, and that's negative e to the negative x. And then we just put it into our formula. So uv, negative x e to the negative x, minus the antiderivative of v du. Okay, let's clean this up a little bit because that's a little bit confusing. So we've got negative x e to the negative x plus the antiderivative of e to the negative x. Well, that we can do. So the antiderivative of negative e to the negative x is negative e to the negative x. And then we can evaluate each piece from 0 to 4. So we've got f of 4 minus f of 0, f of 4 minus f of 0. And then clean it up a bit if you'd like to. Negative 5 e to the negative 4 plus 1. We'll try another definite integral. Back to our Lie8. Do we have a logarithmic function? Yes, we do. So we'll just say right here, u equals ln x, and then the rest of it is dv. All right, take the derivative of u, 1 over x dx, and the antiderivative of dv, we get 1/4 x to the 4th. Okay, then we do our uv minus the antiderivative of v du, ultraviolet, voodoo. Now we've gotten to a place where we know how to take the antiderivative of that. So again, we've got the first section evaluated from 1 to e, and then we took x to the 3rd, antiderivative of that is 1/4 x to the 4th. We've got to evaluate that whole thing from 1 to e as well. There's a lot to keep track of in these problems, so go slowly and keep yourself organized, please. Don't skip steps. So we've learned u substitution and we've learned integration by parts. And sometimes we get to do them together. Okay, so let's look at our Lie8 list. We've got tan inverse x dx. So do we have a logarithmic? No. Do we have inverse trig? We sure do. So u is going to be tan inverse x, and then dv is going to be whatever's left over, which is dx. The derivative of tan inverse x is 1 over 1 plus x squared dx. The antiderivative of dx is x, and here we go. uv minus the antiderivative of v du. Now this guy needs a little extra help, okay? Because we can't integrate him just the way he is. So come over here with me for a minute, and what would normally be u substitution, let's call it w substitution for right now, just because we've already used some u stuff. All right, so just looking at this purple fellow, we'll say that u, or w equals 1 plus x squared. So dw equals 2x dx. Well, that's good. We've got x dx right here. So 1/2 dw equals x dx. So really, we're integrating 1/2 times the antiderivative of 1 over w dw. So we get 1/2 ln absolute value of w plus c. So this is the answer to just that purple part there. And this guy, x tan inverse x, stays in front. And of course, we have to plug our w back in. Don't forget your constant of integration. Okay, this one might blow your mind a little bit, but I want to show you a trick that you can maybe try. So we don't have logarithmic. We don't have inverse trig. We have algebraic, but it's part of the exponent. But that radical is going to give me some trouble. So watch this magic here. I'm going to let w equal x to the 1/2. Just that right there, x to the 1/2. Now, if I square both sides, I get w squared equals x. Okay? Take the derivative of this, of both sides, I get 2w dw equals dx. So now I'm going to rewrite my original function, all right? That 2 is on the outside. And then the dx became w dw. And look at my exponent is just a really lovely single variable. So now on just this part, let's do integration by parts. U equals w, and then dv is going to be the rest of it. E to the w dw, u do. And then the derivative of w is dw. The antiderivative of u do is just u, e to the w. Now we can pop that into our integration by parts. So uv minus the antiderivative of v du, and then e to the w we can easily integrate. So we have 2w e to the w minus 2 e to the w plus c, and then plug w back in. That probably blew your mind, and that's okay. That takes some practice. Sometimes one iteration of integration by parts isn't actually enough. Sometimes you got to do it a couple times. So this one, for example, we've got the antiderivative of x squared cosine x dx. So looking down at Lie-8, we have no logarithmic, we have no inverse trig. We have an algebraic function right here at x squared, so we'll make that u. And then the rest of it, cosine x dx, is dv. So du is 2x dx, and v is sine of x. And we'll pop that into our formula, okay? So x squared sine x, we're good with that. However, this part still needs integration by parts. So we have to kind of start this with another table. So this time u is 2x, right here. dv is the rest of it. And then du is 2 dx. And v is negative cosine x. So we'll plug that into our formula, uv minus the antiderivative of v du. So notice this guy still hanging out here, all right? and then minus uv minus the antiderivative of v du. That's what we have. Thankfully, negative 2 cosine x dx, we can just take the antiderivative of. But what I want to show you is how many times we had to go through this was based on the exponent of our algebraic function. Because in taking two derivatives of x squared, the variable disappeared. So our final answer then is x squared sine x plus 2x cosine x minus 2x sine x plus c. If you need to repeat integration by parts more than just once, a table can streamline this whole process. So this process works well for expressions in the form of x to the n e to the kx, x to the n sine of kx, or x to the n cosine kx. And this is what we're looking for. This x to the n, this n tells us how many times we might have to do integration by parts. So we're going to create two columns, one for u and one for dv. And in the u column, we start with plus, and then we have alternating signs, minus, plus, minus, plus. And our solution, our final answer, is going to be the sum of the signed products along the diagonal entries, which probably makes no sense right now, but let me show you. So looking at what we need to anti-derive, we've got x to the third and then e to the 2x dx. So here's our u, and we're going to have to do integration by parts 3 times. So that's when this tabular method comes in handy. So u is going to be x to the third, and dv is going to be the rest of it. Now, x to the third, let's just take the derivative of that. We get 3x squared, again, 6x, again, 6, and finally we get 0. And that's what we're looking for. Now, for dv, we need to take the antiderivative of that to fill out the rest of the table. 1/2 e to the 2x, 1/4 e to the 2x, 1/8 e to the 2x, 1/16 e to the 2x. Now we start drawing diagonal lines, and you multiply the diagonal. So x to the third times 1/2 e to the 2x. So that's uv. Minus the next one, 3x squared times 1/4 e to the 2x. That's another uv. And we just have to keep going until we run out. 6x times 1/8 e to the 2x, 6 times negative 1/16 e to the 2x, and then the last one would be 0 times whatever came next, so we're done. And we just add our constant of integration. Let's try this one more time. We'll use a trig function. We're going to have to go through this process twice. So u is x squared, dv is the rest of it, and then we'll take the derivative of x squared until we run out. 2x, 2, 0, and now we'll take the antiderivative of sine of 4x until we come to the end of the table. So negative 1/4 cosine 4x, negative 1/16 sine 4x, and 1/64 cosine 4x. And then we just have to start multiplying stuff together. So x squared times negative 1/4 cosine 4x minus these two multiplied together, but we have another negative right there. So that'll be plus 1/8x sine 4x plus 1/32 cosine 4x. We've hit 0, so we're at the end, plus c. uv, and then minus cosine x e to the x. But look see, we're already back to the original function here. So let's stop the madness and let this be our v to u. Here's the magic. This guy, which matches the original function on the left, I'm going to add to the left. So now I have 2 e to the x cosine dx's on the left, and then just the rest of it on the right. Well, if I divide both sides by 2, I can isolate e to the x cosine x dx. And on the right, there's nothing left to solve. So the antiderivative of e to the x cosine x dx equals, right here, 1/2 e to the x sine x plus 1/2 e to the x cosine x plus c. Isn't that crazy? But fun. Your mind is probably swimming. So take a breath. You can do this.